Greetings to the respected faculty. I am Lasya Mandapati from CSC AI&ML B section. My roll number is 24951A6686, and today I'll be presenting on the topic Solving the 5G Mobile Antenna Puzzle, Ac- assessing future directions for the 5G mobile antenna paradigm shift, with the focus on its connection to database management systems. 5G technology represents a major shift in mobile communications. It enables ultra fast speeds, low latency, and connectivity for millions of devices simultaneously. However, these capabilities come with an explosion of data generated by antennas and network infrastructure. Every antenna continuously records signal strength, user density, and mobility patterns, as well as environmental conditions. Without an efficient DBMS, this data would overwhelm the system. Database, database systems ensure structured storage, fast retrieval, and real time analytics. 5G is the fifth generation of mobile communication designed to support enhanced mobile broadband, ultra reliable low latency communication, and massive machine type communication. It enables applications such as autonomous vehicles, smart cities, and industrial automation. These applications generate massive data traffic, placing unprecedented demands on infrastructure. Traditional systems cannot handle this scale efficiently. Therefore, advanced data storage and distributed DBMS architectures are required to support 5G operations. Antennas are the interface between digital networks and the physical world. In 5G, antennas operate at higher frequency and require precise coordination to maintain signal quality. Unlike previous generations, 5G antennas are dynamic and adaptive. They constantly adjust transmission patterns based on real time data. This requires continuous monitoring and data collection, which must be stored and processed instantly. Thus, antenna performance is tightly coupled with database systems that support high speed analytics and decision making. The shift from traditional antennas to smart antenna arrays represent a major technological transformation. Technologies such as massive MIMO and beamforming allow antennas to focus signals towards specific users rather than broadcasting uniformly. This intelligent behavior is driven by data. Antennas rely on historical and real time data sets to predict optimal configurations. This creates a feedback loop where antenna efficiency depends on fast and reliable database operations. The paradigm shift is therefore both a hardware and data revolution. 5G antenna systems face significant challenges. High frequency signals weaken quickly and require dense infrastructure. Energy consumption increases as antenna networks expand. Another major challenge is handling real time data streams. Antennas produce continuous telemetry that must be stored, analyzed, and acted upon instantly. Traditional databases are not optimized for this scale. This pushes DBMS research toward real time distributed systems capable of processing high velocity data. 5G antennas generate multiple categories of data: signal metrics, user mobility, traffic load, hardware status, and environmental feedback. This data is essential for network optimization. The volume of this data resembles big data systems. It requires scalable storage, indexing, and analytics. Databases must support high write speeds and concurrent queries. This makes 5G networks one of the most demanding real world database management system applications. Database management systems acts as the backbone of 5G infrastructure. It ensures reliable storage, distributed access, and real-time analytics. Modern 5G networks rely on distributed databases to prevent bottlenecks. Data consistency and availability must be balanced carefully. Database management system techniques such as replication, sharding, and distributed transactions become highly essential. Now, databases in 5G must be scalable, fault tolerant, and low latency. They must handle streaming while maintaining consistency. Traditional relational systems alone are insufficient. Hybrid architectures combining SQL, NoSQL, and time series databases are often used. These systems must operate continuously with near zero downtime, reflecting the critical nature of mobile networks. Modern 5G antenna systems rely heavily on data driven optimization. Every antenna continuously collects performance metrics such as signal strength, traffic density, user movement patterns, and interference levels. This data is fed into database systems where it is analyzed in real time. Using advanced analytics and database and machine learning integrated with database management systems, the system can dynamically adjust beamforming directions, transmission power, and frequency allocation. For example, during peak traffic hours, antennas automatically prioritize congested areas based on database insights. Predictive maintenance is another important application. Historical data stored in databases allows operators to detect early warning signs of hardware failure. Instead of reacting to breakdowns, networks become proactive and self optimizing. This shows that in modern 5G networks, antennas are no longer passive devices. They operate as intelligent, data driven entities supported by high performance database systems that enable rapid decision making and continuous optimization. The future of 5G antennas is moving toward fully autonomous and AI driven networks. Smart antennas will increasingly rely on artificial intelligence models trained using massive data sets stored in distributed databases. Self optimizing networks will automatically adjust coverage, power usage, and traffic routing without human intervention. This requires DBMS platforms that can support AI workloads, real time analytics, and continuous learning. Another future direction is energy efficiency. Intelligent antennas will use database driven analytics to minimize power consumption while maintaining service quality. Sustainability is becoming a major design priority. Edge computing will also play a key role. Instead of sending all antenna data to central servers, local databases will process information closer to the source. Edge computing represents a major architectural shift in 5G networks. Instead of relying solely on centralized cloud bases, data is processed near the antennas using distributed edge databases. This reduces latency because decisions are made locally rather than waiting for the central processing. For time sensitive operations such as beam steering and traffic balancing, milliseconds matter. Edge DBMS systems enable instant responses. This combination of edge computing and distributed DBMS creates a resilient and scalable infrastructure capable of supporting future 5G and even 6G systems. Security is a critical concern in 5G networks because antennas handle sensitive user and infrastructure data. Database systems must enforce strict access controls, encryption, and authentication mechanisms to prevent unauthorized access. Data integrity is equally important. Incorrect or corrupted data can lead to poor antenna decisions, network outages, or even service degradation. TVMS ensures integrity using transaction management, consistency rules, and auditing systems. In conclusion, the evolution of 5G antennas represent more than hardware upgrade. It is a shift towards data driven networking. Antennas now operate as intelligent systems that depend on continuous data collection and analysis. Database management systems form the backbone of this transformation. They enable real time storage, analytics, optimization, and security. Without the advanced DBMS technologies, the full potential of 5G cannot be realized. As networks become more complex and automated, The integration between antenna systems and intelligent databases will only deepen. The future of mobile communication is not just wireless, it is fundamentally data centric. Thank you for your attention. This concludes my presentation on solving the 5G antenna puzzle and the role of database systems in supporting this paradigm shift. Thank you.